right, so let's get started. Hello everyone. My name is Robert Cashman. I'm happy to host today our speaker. Patricia Alves-Oliveira is an assistant professor at Michigan, and she's also an advisory board member at Meta. She leads the Robot Studio, which is a research lab that dedicates to the advancement of human augmentation through the idea of embodied social intelligence, which will be a lot of the talk today about. She focuses on designing robots that kind of like develop the ability to understand and support human preferences, and she focuses particularly in the space of healthcare. Her work bridges human-centered robot design, embodied AI design, and also real-world evaluations, and she develops novel type of robotic hardware and also context-agnostic algorithms. And she does this while integrating into everyday life and into a way that you can think of robots socially becoming a bit more intelligent and having more intelligent ways. Patricia, just a background, she was a senior UX designer at Amazon Lab 126 in California, correct? That was. And there she worked on a platform called Astro, which was Amazon's first home robot that they developed. She was also a postdoc at UW in University of Washington, and she received her PhD from the University Institute of Lisbon, and she also spent time at Cornell. She got Best Paper Awards, 3 of them at ACM IEEE for Human Robot Interactions Conference, and she's also co-founder of Talking Robotics and has been recognized with multiple awards. Rising Woman Star in Social Robotics, ECS Rising Star, and also Future Digital Leader. And with this, I would like to hand over the words to our invited speaker. Patricia, the floor is yours. Thank you.
Thank you, Robert, for the incredible introduction. I don't know what else to say about me. And for being here, I'm very glad to be talking to you about embodied social intelligence today. So I'm going to dive right in and just going to give you a little bit of my background, in other words, with a bit more nuance. So I did my undergrad and master's in clinical and health psychology in Portugal. And then I ventured to Cornell University and Technical University of Lisbon with my PhD in an interdisciplinary field of computer science and aerospace and mechanical engineering, where the application domain was human-robot interaction. So I was really interested in people and in interactive systems. And these 2 degrees led me there. Then I went to Seattle at the University of Washington for postdoc during 2 years. And then now I'm an assistant professor at the University of Michigan in the Department of Robotics. Throughout my academic journey, I also spent some time at Amazon. This was actually after my postdoc because I had a little professional crisis. I didn't know what I wanted to do, if I should continue as an academic or if I should move to the industry. So this gave me a really good experience there. I was there for more than a year. I really enjoyed it, but I also missed a lot of the academic world, so I returned. And now I'm involved with Meta on the advisory board for the new council they have. I'm also advisor for OpenStyle Lab, which I'm going to tell you a little bit more about. But my building looks like this at Michigan. So every time, if you find yourself in Detroit area, do let me know. I would love to tour you around our building. It's called the Robotics Building because guess what? Ford financed it. And we have a robotics program in undergrad, master's, and PhD. So we graduate students in robotics. Robotics serves as a department with a specific curriculum. My lab is called Robot Studio, where I have students from the College of Engineering, but also from other domains. We are very interdisciplinary, including philosophy, psychology, arts, and other fields according to the project needs. And right now, I'm an academic guest at ETH since January. So I came here and the weather was crazy bad, and now it's been better and better. And as I mentioned, I'm also at Meta and at Amazon. I was working on this robot. I just wanted to give you the looks of it. It's the first Amazon home robot, and it was deployed and you could purchase it at Amazon.com. They now removed it, but yeah, I was a designer for it, so I designed a lot of how the robot should interact with families, given that every family can be different at home and every home is also different. At OpenStyle Lab, I work with people with disabilities. This is a non-profit organization, and they want to introduce more technology on how people with disabilities are thought about in the fashion industry. So today I'm going to talk to you about embodied social intelligence. There has been a lot of important developments in mechanical intelligence. Indeed, we needed, mechanical advancements to make robot systems better. Then artificial intelligence now is at the forefront because we need to make robots do smarter things for us. But today I want to tell you more about social intelligence. And social intelligence is something that is really important to humans, because the idea of relationships is part of our life. And this is known since Darwin. You might be familiar with the book The Origin of Species, whose main premise was that survival comes from adaptation to the environment. But later on, what less people know is that Darwin updated this theory in a new book 12 years after, called The Descent Man, where the main premise there was to associate survival with communities and relationships, with cooperation, empathy, and moral values. As humans, we are wired to connect with each other, and this was shown by this beautiful psychological classic experiment in 1944, where participants were invited to watch a video like the one you see here, and at the end, their goal was to tell the story of this video. And the results show that participants created a story full of descriptions of social meaning, coming only from watching these very simple and minimalistic shapes. For example, the large triangle was almost always described as an aggressive bully, the small triangle and the circle seen as more passive, and the circle described as being afraid or trying to escape. What is really striking is that we are wired for these social connections and relationships. And this is actually generalizable from very early on to machines and other systems that are non-humans. Reeves and Nass, both professors at Stanford, wrote one of the first books about this in '96, called The Needy Equation, where they claim that interactions with media are identical to social interactions between people. I mean, this is why we are polite towards computers or chatbots. There are people marrying them. We name our cars and we can care for our phones like they are a baby. There is a huge power in working with technologies that have some interactivity and daily intimacy with us, because they can really impact how we live our lives and how we build our relationships. The reports you see here emphasize not only the market growth in robotics, but a striking growth in creating relationships that these robot systems can have with humans, other species, and even the environment around them. So this is true, and we can see it in many ways in education. For example, at EPFL, there was a team that created the Now robot that is teaching children how to better handwrite. Then we have the Moxie robot in the US deployed in Texas Hospital that is helping nurses deliver supplies to patients. We have robots coming to the warehouses and working closely with humans. I would say warehouses are still a big challenge, but there is the desire to have humans and robots coexisting and working towards the same goal. And we go far beyond Earth to space, where NASA is interested in creating robots for spaceship missions that can help not only the mental health and accomplishment of tasks of the crew, but also to be an agent in these tasks. So what I'd love for you to take from this class today, or this lecture, is that I believe the future of robotics are in the successful relationships they can create with other people. In my lab, we work on creating these relationships using this framework that involves 3 stages: designing, building, and evaluating these robot systems, and iterating around this framework, of course. So what is foundational in our research are the types of methods and assessments we use. So in terms of methods of design, I rely a lot on human-centered robotics methods, where we involve people in the co-design of robots, speculative design, ethnographies, and then we build these systems taking into account the knowledge we gathered. So we can involve, low fidelity prototyping, but also other methods more computationally related. And then when we have built our robot system, we move on to evaluate how it performs in the real world usually. It can also happen in the lab. And we use a set of mixed methods from quantitative to qualitative, such as behavioral observation surveys, but also logs from the system itself. And then the communities that my lab works on are different according to the stages of their projects. And the application domain that we have is currently in physical and mental health, because our goal is really to better human health with our work. So I like to say that in my lab we create robots that people love, but that they don't fall in love with, which is a very important distinction. And you can see here there has been different platforms I've worked with and different projects. And I want to talk to you about a lot of them, but today I chose 3. So one project is a full stack project that you will see from beginning to end. The second project and the third one are newer projects in the lab. So I will tell you about robots for creativity. So the goal of this project was to create a robot that would engage children in creative process. And you might ask, why? Why creativity? Creativity is actually really important and has been recognized by numerous institutions that is a mental health indicator. However, the classrooms of the past would look a lot like this, and education was a lot about memorization and standardization, which matched the skills needed to fit and operate in the industrial world. A lot of the tasks needed to be repetitive, right? But nowadays our workplaces look like this, or they inspire us like this. If you, for example, look at job descriptions of current industries, there will be a point where you need to be an innovator or to, bring something new to the team. So creativity is now part of what we want people to have in their jobs. But the classrooms of the present still look like this, actually. And so how can we match the way children learn with the skills that they need to operate later in life? That was the main question that I had, which led me to the research question of how can I support the creativity of children? And I know I couldn't change the modus operandi of educational systems, but I could contribute with a tool to include in those systems. So I decided to create YOLO, this robot that you see here. It's a 12 centimeter height robot. It has these abstract looks, doesn't look like a humanoid, doesn't have a front or an end. And it served as a character that children would use during the creation of a story. The difference is that this robot would also provide ideas for the story, which is very different than a traditional passive toy. But let's look at how robots are developed right now, because design is one component of my work. So adults are developing robots for children, and usually children are kept aside of the development of robots. But why is that? Why are children not included more often? Let's look at a few reasoning ways. So one sample representation, it's really difficult to find just children out there, right? We cannot just go to the playground and say, hey, come on here, build a robot with me. They are protected by this ecosystem of schools, parents, and other ethical values that we need to go through to access them. But even if we can access children, then we have the problem of data collection. How can we collect data from these children? If we use the collection data methods we have with adults, like questionnaires or interviews, they will not be really profitable with children. We will not get the information we need to build our robots. But even if you've solved these 2 problems, you have still the third challenge, which is the actionable input. If you collect data from children, how would that map into the robot or the algorithm you want to design? So doing child-centered robotics is actually a very difficult and hard challenge. So to address this, I chose to focus on this double diamond design process model. It's called double diamond because it has 2 diamonds divided into 4, and it's a theoretical foundation for designing new technologies that I used. So this project took about 2 years and involved more than 140 children across Portugal and the US. And what I want to do is to tell you how I used this to create YOLO. So the first thing I did was a phase called Discover. So what I wanted here was to really get insights into my problem. I knew very little about children and creativity. So I did a systematic review to understand if there are practices validated by psychologists that stimulate creativity in children, and I discovered a few. Then I did interviews with domain experts where these were improvisational teachers and dance teachers for children, where they were telling me how they engage children in creating things that are more creative. And they kind of mentioned these two techniques, contrasting and mirroring. Contrasting is when they prompt for a different thing, and mirroring is when they want them to imitate behaviors to the very end. So kind of like extenuating the how many things they can create out of just one single stimuli. And I want you to keep these two in mind because I'll get back to those. The third thing I did was to go to a school and just sat in a corner of a classroom and just observed how children play. And there was a common thing around this, which was they are storytellers. Everything they do implies a story. That's how they understand the world, that's how they make meaning out of things. So you can see here two girls puppeteering these two cubes, telling a story to the boys on the left. So I kept this in mind, and specifically I wanted the task to be about storytelling. The second stage was define. So this is when I had collected a lot of information in my previous stage, and I wanted to converge now on some actionable things I could do for my robots. So I engaged into co-design with children. And the first thing I did was a method called body storming. So I wanted to get insight into the behaviors of the robot. So I told children, I prompted them to act out only with their bodies, not using voice, for certain emotional cues. So here you can see grumpy. I told them, act as if you were grumpy. And I wanted to use kind of these footages of their body to inspire the creation of movements for my robots. But as you can see, this is highly complicated because the human body is full of degrees of freedom, and I was not into a humanoid because that's a super complicated task. So I moved this task, I adapted it to a 2D plane. So I laid down a big piece of paper on the floor and I asked children exactly the same prompts. Move this cube, which are the ones on the top left, as if the cube was grumpy or happy, and I continued giving emotional cues until I found some patterns that they created with the traces of the cube on the paper. So the more curvilinear patterns were always associated with more positive valence emotions like joy and things like this, and the more spiky and rectangular ones with negative emotions. So I basically trained my robots to recognize these emotions when it was being moved on the floor by children, so that we could know the emotional state of the story they were creating. The third stage was called develop, and this is when I did some work on the prototyping of the robot. So one of the things that I wanted to know was the size that this robot should have. And I wasn't sure because I wanted a robot that children could grab and go like they do with their own toys. And at the time when I did this research, most of the robots for children were tabletop robots. So basically you have a robot on a table plugged into a wall for power, and you sit and you talk with it. So it's a very passive interaction, and I wanted to mimic how children generally are in their lives. So I did this study, and what I did here was I put clay around the robot, and I asked them to create a story with each of these 3 different prototypes. And the fingerprints on the clay gave me an idea of how comfortable their grasping was on the different sides of the robot and what was the most suitable size for them. This was very important because engaging children, they usually want to correspond to your expectations, so they want to make everything right. In this task, there's nothing to do right, they just had to create a story. So they wouldn't feel judged and they would act normally. So the envisioned size here was something between the medium and the large size. And you could wonder, how does YOLO look like what it does? Why does it have that shape? So if you remember that puppeteering activity with the cubes, that activity led to a concavity in the cube just because of their little hands trying to grab it. And what I did was just I extended that concavity up and inwards so that the shape of the robot was more graspable. And that's kind of how YOLO became what it is. But just for the sake of a timeline, there was a lot of prototypes, there was a lot of more activities I did to understand what better robot would fit children. So you can see I started with some sketches, I did some paper prototypes, some actuated robots as well, then I did the study for the size, and then I reached my final robot. So what I think is interesting about YOLO is that it's a self-contained robot. Everything that it needs is inside it. And then it's also a simple robot in a way, because the only sensor that it has, it's the movement sensor and a touch sensor. So when children are touching the robot is recording the movements, but it's not moving. And then when they let go, the robot can either do a contrasting or a mirroring technique to practice creativity with children during storytelling. Then it has some lights at the top, just for emotional expression. And the optical fibers are just a petting behavior to familiarize children with the robot. They are not actuated and don't really have a bigger purpose. So the next stage was deliver. So here I really wanted to understand if this robot could increase the creativity of children. And I didn't know that, so I had to do a study for this. And this was really important because that was my initial goal, to create a robot that would stimulate that creativity. So I conducted a study in school with my robot, my final robot that I considered good enough to go for a study. And I had this question: can my robot increase creativity during play? So 62 children played with YOLO, created a story, and I had the traditional procedure of having a pre-test, the intervention where they play with YOLO, and then a post-test, and I also recorded the interaction for some behavioral analysis. I had 3 study conditions, so I could compare the creativity levels. So the first condition was a simple, I called it a simple condition. It has some creativity behaviors, which I'm going to tell you in a moment what they are. The second condition had the same creativity behaviors, but also some proactive behaviors, which just meant that if children forgot about the robot would move around a little bit after a few moments to engage them back into the interaction. And then the control condition, where robot was turned off. It's kind of like a normal toy, but I wanted to keep the embodiment the same. So in terms of the creativity behaviors, this girl here is moving YOLO in a zigzag shape. YOLO is recording this and applying the contrasting condition by moving in a different direction. This boy is doing a straight line and YOLO records and does the same. Now thinking about a storytelling context, what happened here was she was saying, the robot is going to school, and then YOLO does this. So she continued, wait, someone is at school that is fearful, that is triggering fear in YOLO. So when the robot does a contrasting movement, it basically triggers a different storyline. It triggers a divergent thinking cognition. When the robot does the same movement, it elaborates on it. So in the case of the boy, he was saying the robot is going to the grocery shopping, and then YOLO continued going to the grocery shopping to get strawberries. So this is kind of how it enters in the story. So then I compared my results from the pre-test to the post-test, and I saw that across all my conditions, creativity increased, which was kind of disappointing because it just means that telling stories increases their creativity. It didn't tell me that my robot in my condition increased the creativity more than in the robot that was turned off, right? So I was pretty blown away, but I didn't give up. I went on to do some behavioral analysis. So I looked at each of the videos of the stories that were created, and I coded each portion for these coding scheme. Originality, how rare the ideas are. Flexibility, how different are they from each other. Fluency, how many ideas are there. And elaboration, how much detail do they contain. This coding scheme is in the literature of creativity. It was not created by me. I relied on theory here. And what I found was that in the conditions where YOLO was interactive, so in the simple and enhanced condition, the creativity, the originality of the stories was higher than in a condition where the robot was turned off, the control condition. Which basically means that the creative process of telling a story is more rich, unique, and rare when they are exposed to a robot that can co-create a story with them. This was one of the first, at the time, handmade robots for creativity that involved children from the very beginning to the very end. And I've learned a lot with this project, so actually I put all the materials in open access. So all the hardware of YOLO is in open access. I conducted, videos here and there for tutorials, and I made a very descriptive thing about YOLO, which I'm now very happy to hear. Sometimes I receive emails of people saying they're using YOLO on their classes. So this concludes my first project, and I just wanted to take a moment here to see if there is any questions around it before I move to the second project. Yes?
Yes, I have a question. So if you have
different sort of nationalities or different ethnic backgrounds that might react to. You were saying there's the zigzag versus the round motion, and it might evoke different emotions in some way. Is this sort of like universally applicable across cultures, across these groups, that you would see this observation, like the zigzag versus, or like these reactions to it? Or do you think it's different if we were to go somewhere completely other continent?
Yeah, so when I did the study for the emotions to understand what was going on in the story, I tried to derive basically the emotion primitives, so more rounded, more zigzags, and then capture what children were telling in their stories. In the children that I tested this with, it was true that in the majority of the cases, negative valence, so more negative emotions, were associated with more spiky or squared types, not rounded. So I think we could assume, we could do better testing of this, but I think as a preliminary pilot result, we can assume that this was working well. Also, when we did the deployment of robot yoga in school, it was reacting to those things, and it was flowing well in the final story that was created.
Thanks.
But I think for a general universal way, we would need many, many more children from different cultures. Yeah, and I just did 2, US and Portugal.
Was the creativity increase of your robot ever independently evaluated? Because it looks a lot like you did something, you didn't get the result you wanted, then you changed the measurement metrics so that you get what you want, and that's the story that you're telling. But did somebody go and evaluate independently whether it has an effect?
Yeah, that's a great question. So basically for the, I have a hidden slide here that I can show you. Let me just bring it on. Okay, yeah. So what I did was not to look for results where they existed. I conducted the study from the beginning the same way, which meant that I applied a creativity at pre and post test, the creativity measure, which was actually this one called CREA. This is a verbal creativity measure because my task was on verbal creativity. They were not painting, right? They were telling a story. This creativity is meant for children and was developed by Corbalan, who is a psychologist, developmental psychologist. And what they have to do here is they see this image and you ask them, ask as many questions about this image as you can think of. So they can ask, what is this? That would receive the score of 1. They can say, is this a phone handle or a shower handle? This would receive a score of 2 because they are giving 2 cognitions for what it could be. So according to that, you measure their creativity score, and you do that at pre-test. Then they'll play with YOLO, and then I do the same with a different image, form B, for post-test. This resulted in differences between conditions that were not statistically significant, which means they increased, but not between the conditions, right? So that was just one measurement. The other one I had was the recordings. So I started looking to the recordings. And thankfully there I found something. I could maybe not have found anything, but I did. And I only found for this coding scheme of originality. I did not find for flexibility, fluency, or elaboration. So these things were done independently, and the coding scheme when I coded the videos was with a second coder. So I had another person coding exactly the same videos as me, and we rated our interjudgment agreements.
Okay. Thanks.
Thank you. I'm going to move to the second project because I think I have still time for that. So I would like to tell you about robots for mental health, which I'm very passionate about because mental health is a fundamental human right. However, and very sadly, we have news such as this one, where teenagers still engage in ways with technology that can be very detrimental and even lead to suicide. And this tells us a lot about how our technologies are designed, but it also tells us that we have a mental health crisis. So we know that more than 1 billion of people are living with mental health disorders, and anxiety and depression are the most prevalent disorders. And adolescents in themselves are the population that bears most of these problems, and suicide remains the leading cause of death among youth. Let's just land here in this information for a moment. Suicide remains the leading cause of death among youth worldwide. This is huge. And I was actually reading a little bit about Switzerland, and access to mental health services around the world, not just here, are one of the most significant barriers to accessing mental health, which is the same in the US where I am, it's the same in Switzerland, and it's the same in so many countries. This is just for the purpose of situating the talk here. So the point of this project was to develop a mental health robot that would live in a school and deliver micro-interventions to the youth on demand. Micro-interventions are defined as very short interventions with an immediate positive effect on the mood. And I want to show you a clip from a very cool, I think, show called In Treatments. Just look at it and pay special attention to the psychologist, this one. So he's nodding, asking a question. This is the patient. And he goes on and nod again. And she continues to talk. So, what's a really important behavior in therapists is active listening. The act of being there while you talk to them, which can be translated into nodding behaviors. So I was very interested in understanding how that simple behavior could be applied to mental health robots to improve a conversation around mental health. So the goal of this work was to really develop and improve back channeling behaviors. Specifically, we focused on nodding during a conversation. So we engaged in data augmentation for this work, to enable a platform like this one, Curie, to have a more robust nodding behavior. So the model we came up with was a recurrent neural network that maps sequences of input from the speaker to the actions of the robots. So it's a combination of 3 features. 2 of them are acoustic and 1 of them are visual. The acoustic feature augmentation is performed by warping them across time and masking blocks of utterances over time. And the visual one is performed by wrapping the head pose in space and time. So for example, the acoustic augmentation on the left, and then the same feature with warping on the right. So to do this work, we had to collect human data. So we recorded audio and video of 2 people in Zoom interacting with each other. And each interaction was structured around prompts, very specific prompts. So one person was tasked to respond to the prompt, while the other person was tasked to perform back-channel behaviors to signal they are listening to the first person, to the talker. So you can see some examples of prompts here. For example, tell me about the most fun memory from last summer, or teach me how to cook your favorite dish. So kind of different balances of prompts, which are things that can come up in a conversation with a therapist. We had 84 interactions and 12 participants, and we trained our network, and our results show that data augmentation achieved the highest performance across the validation set. And then a qualitative analysis of 2 examples, or 2 unseen examples below, can also show you that the LSTM has basically in the left side very infrequent head nods, and when we do data augmentation, it corresponds more to the ground truths. And the same is true for the one on the right side, where it has 2 frequent head nods, which is balanced out when we augment data, and it's more balanced to the ground truth. So we then deploy this into the robot, and we had 102 participants interacting with it and being prompted to tell stories like the ones in our data collection. We had these 3 conditions, so we had the learned condition, a rule-based and a random, and we did a within subjects design, which meant that each person interacted with the 3 conditions, so we could compare. So the results of our study showed that the perception of our data-driven back-channeling behavior was positive, with a forced choice of questions eliciting more natural behavior. So this is sustained by some of the quotes of the participants. The robot seemed more natural and normal, or it felt like it was really listening. So gathering this, how could we use that to augment access to mental health among the youth population, which was still the population we wanted to work with? So we started looking at therapies just for teenagers, and we encountered the dialectical behavioral therapy or short for DBT. It has a very complex name, so let's call it DBT from now on. And it's composed of these 4 parts. And only when these 4 parts are there, you can call it a DBT therapy. There is a pre-assessment, there is group training with other people, other youth, there is individual therapy, and then there is home coaching. And looking at home coaching, when we interviewed some of the DBT therapists, they say it's the one that is more problematic. Basically, it has low engagement. Home coaching means that the youth has some exercises to do at home. And one of them is worksheets. So when they are facing a state, for example, they are sad, they are invited to go and open the book and do a worksheet that could help them. So the worksheet is generally divided into exercises. All of them follow the structure of an explanation. So they read the explanation, they read an example, and then they do an exercise in the workbook. But this has a low adherence, a low engagement, because teenagers say that it's not very conversational. So basically, when they feel sad or anxious, they want to call their friend and go for an ice cream and not go in front of a workbook. It feels like a test, but it is what therapists have to help them at home. So we don't want to substitute therapists. This is a very important disclosure. What we're doing here is to translate the worksheet content to a robot to make that part more engaging for the therapy. So we engaged in sessions with the youth to understand how this robot would look like to interact with them at home. So we had 20 teenagers coming in and engaging in these design sessions. And what we found was that there was no way that we could kind of cluster all of their ideas into one robot, because all of them were very different. These are just a few examples, so there was no one size fits all. And that is really matching the adolescent population, because they are forming their identity, they want to be unique, and everything they do is very personalized to the detail to them. The stickers they put on their phone, everything, their hair, their clothes, their branding, right? So we had this in mind. How can we build a robot that, fits all without having that premise from them? So we started to do some sketches of many things that the robot could do, and we landed on this idea of just developing the bare bones of the robot that teenagers then could customize at home to fit and look whatever way they wanted. But the intervention modality, so the content the robot would deliver, would be the same, created with psychologists that are trained in DBT. So there was a participatory design element with teenagers for developing the character, kind of how the robot looks and feels to them, and you can see here in the end-user programming side of things that they're doing different things. And then therapists were brought in to develop more the content for the intervention. So exactly what the robot should say to the children. And we ended up with a robot deployed in children's houses that looked very differently. So I'm going to show you this is one example, but then the robots they created were very different in each home. So to understand if we really were able to do this, we deployed the robot, and we did this study with 19 teenagers from 16 to 18 years old. And the duration of the study was 2 weeks. In the first week, they had the robot to interact with daily that would deliver these micro interventions that are a substitute of the worksheets. Now they wouldn't go to a book, they would go to the robot. And in the second week, they would go to the book. And we had 2 groups, so we randomized where they started. The group 1 would start with the robot, move to a workbook. The group 2 would start with a workbook and move to the robots. So our results show that the level of stress decreased among them with the robot and with the workbook, but they were able to engage more with the robot in a more natural way. So they developed mental health routines. Things they mentioned was, I knew that after my breakfast I would go and talk to the robot, which this routine was never very established with a workbook, which meant that it was harder to sustain over time, it had low sustainability. They also felt that the robot was good to interact with, but different than a friend or a family member, because it didn't have this judgmental ability. It was more a neutral interaction for them. So we also put everything in open access about this robot for more people to use. And I'm just going to stop here for maybe 1 or 2 questions, and then I'm going to move to my last project very quickly. Or I can have questions at the end as well. Yeah.
I was curious, if you think of this mental health issue that's coming up, the more, at least my observation, the more we are connected to screens, and this involves screens versus the piece of paper. Is there a way of also correcting in the study? Like our addiction to screens is getting more and more, the way that apps are being designed. How much did you find this in your study as a factor? Like it's also an attractor, so it was overall more positive, it looks like, right? To have that animated screen. But how far does it go before it becomes problem?
I think this is a very important question, and I think it's related to what screen time is. And screen time is not just being in front of a screen. They could be in front of a screen, but having a very positive side effect. For example, if they have an interaction with, grandma that is in another country, right? It's very different than just watching passively a movie. So I think screen time is a big thing, but what I didn't bring here, because I don't have enough time, but I can tell you very quickly, is that this was an at-home study. We also deployed this robot in school, which was our initial goal, and we discovered that girls specifically, they would come to the robot in pairs at least, or 3. So the concept of, privacy and individuality at that age is to go with their best friend. And they would do that together, and then they started to tell other people, and they were coming as well. So I think it had a good effect, it had a positive effect. Now, I don't know if we had left the robot for more than 2 weeks in the school, if this would continue on, or if this was novelty. That's something I'm very curious about. How sustainable are robots in mental health across time? But I think the study kind of indicates that it is promising. It is a promising technology.
You have until quarter past.
Okay, so I'll go to my last project. This project is about robots for pediatric OCT. OCT is this machine you see here, optical coherence tomography. We'll call it OCT for simplicity. And it is a project that is still in development, so we actually don't have many publications yet, but I trust you. I trust this audience that you could be interested in this. And it's about how to do these eye exams for children. So, can I ask if you did this already, an exam like that? Can you raise your hand if you did it? Yes. Yeah. And I see other people with glasses, so I assume you also did it. You didn't just go buy your glasses. So this is a very common exam. And it's done because vision is one of the primary ways we perceive and sense the world, and we want to keep our vision healthy. Especially for children who are developing, having a healthy vision is really important. However, testing for the healthiness of their vision is a challenge, and which means that there is a lot of children that undergo eye conditions without being diagnosed, because OCT is a device that can scan your eyes to see how healthy they are, but it involves the cooperation of a patient. The patient has to stay with their chin and forehead still for a couple of moments so that we can scan the eyes, right? So imagine doing this with this child. It's very difficult. So OCT, basically, what we see is that it takes these cross-sectional images of the eye, capture different levels of the retina and other structures in very detailed information, and patient collaboration is really important. However, we know it's really difficult with children because what happens is that they either don't stay still because they're bored, or they are afraid of the situation. And this means that a lot of times they have to go under anesthesia in the operating room to make an OCT exam. Doing that is a very dangerous procedure too, that not every parent wants to do. So this results in them going undiagnosed. So we're working with the Kellogg Eye Center, which is a Michigan Medicine ophthalmology clinic, and we interviewed a few technicians and doctors there, and this was the agreement. OCT exams fail with children because of the reasons I told you. And then we were trying to understand, where do they start to fail? Is it when they enter the room to make the OCT exam? But actually what happens in this storyboard is that basically at home, they are already told they're going to a doctor. So some children can be afraid as well. From that moment, they go to the doctor, they have to wait in the room, in the waiting room. Sometimes this wait can last between 1 to 2 hours in extreme cases. So they are already kind of fed up of the waiting. And then they enter the room with the doctor, and this is when they don't have more patience for anything, and they have to do an exam, and this is why it usually fails. So to cope with these moments, doctors use these strategies here. So they try to put lights or animals behind those CT machines. So if the CT machine is here, the animals would be here, and the child would be looking in this direction to engage them into looking at the target so they can scan their eyes. But this is only possible for a few seconds and they disengage. So basically, we're working together with the clinic to understand if we can recast this OCT machine into a robot as a child-friendly character. So what we did was to put into this robot here the same end effector as the scanner. So and that portion is performed by a clinician and a roboticist in the team. And we can scan their eyes and allow for some movement that children can have because the robot can refocus and target the eye. So this means that the number of scans we can have of the eye is higher, and therefore we can have a better vision of, we can have a better assessment of their vision. So this is kind of what you see if you are with robots. So it goes and scans the eyes, and you will see that this person here, just for demonstration, this is a healthy adult patient. We are not testing children yet. It will move slightly, but you can see that the robot can still target the eye part that it needs to continue with the exam. And the interesting thing is that children can be lying down, so very small children can be laying down, and we can still do this exam to them. They don't have to be standing with their chin and all of that. So you can think of like 1 year old, 2 years old, or even less. So this is what they would see if their eyes is being scanned. Yes, it is true. I agree. So what we're trying to do, so the first step was to try to put the same technology of traditional OCTs into a robot, but now we need to move forward because this doesn't work by itself, and we're trying to understand if we can create a character. So you can think of, Pixar meets OCT exams or something like this. So we got inspired by some cartoons that children like underwater, and then we developed this all knitted robot that as soon as they touch it, it would inflate and kind of, have this behavior of inflation and deflation. But this was just a very preliminary testing, not at all deployed in clinic, just to get our creative juices going. What we're doing now is to be in clinic with the patients and try to understand what characters they would prefer by showing them different things. And we're going to move from there. So this is just, we're now starting the production of the character in the robot and trying different ways to keep this clinically deployable. So we need to choose materials that are easily cleanable and hygienic. And if we want to have more characters to be able to swap, because I know CT exam usually is not done just once in your life. You keep doing it, and especially if you have a problem, you need to do it quite frequently. So we need to continue engaging the child, and for that we need the character to either change or evolve. So this is the last project I wanted to bring you. I'm just going to flash some other projects that are going on in my lab. So I'm working on physically assistive robotics as well, where we're developing robots that can help people in social dining. So if you are in a restaurant, can the robot be brought in to help someone in a wheelchair the same way that a baby seat comes in when you have a child? And there's a lot of work on individual dining, in solitary dining. My lab is not the first one doing work in this field, but we're specifically looking at social dining and how we can have a robot in a public setting like a restaurant or bakery delivering food to people. We're also working on authenticating artist-robot artwork. As you know, creativity is booming, and a lot of people are concerned that what we have now as a creative cognition can decrease with the use of AI or robots. And so what we want to do here is to authenticate when an artist and a robot create a canvas together, if we can distinguish which brush strokes were performed by the artist and which ones were performed by the robots, and which ones were one on top of the other. And we've done really interesting work on this domain, where we had several canvases that we were able to authenticate. This work is under review, but I have an archive publications in case you want to check it out. And the main goal here is to authenticate the artist and to be able to give them ownership even when they use AI, or when AI is trying to use whatever they did, whatever they produced. Finally, we just got funding from Japan to do this very interesting project on shipyard outfitting. So outfitting a shipyard is basically the installation of these wires, pipes, machinery, and internal fittings that are not structural steel in ship. They're also called distributed systems, and it's really hard to do. And so what we want to do with them now is to understand if a robot can augment some portions of this shipping outfitting. And we haven't really started because we just got the funding, but I'm very excited to start going to shipyards and look into this. Besides my research, I'm very excited to teach. I developed 2 new courses at the University of Michigan. One is designed for HRI, for human-robot interaction, where I teach the human-centered methods to develop robots or robot systems that are based on human preferences and human needs. And the other one is the evaluation of the system. So if we already have a system, how can we evaluate the success of its deployment with users in combination with the system performance? And I hope one of the big takeaways you can get is that relationships are really important. We will be interacting with robots as we are interacting with so many other technologies. So we need to think of safe ways to do that match our preferences too. This work could not have been done without my amazing students at the University of Michigan and my sponsors. And also, I'm accepting and very open to collaborations and internships with students from here, if you're interested. So you can come talk to me at the end of the talk about that, or it should be an email. And yeah, thank you so much.
Are there questions? I've already asked a few, but I can ask more if you want. But I'm sure there's other people that have questions. Go ahead, don't be shy. I was wondering, for the shipyard example that you were giving, this is going to be about figuring out how a robot supports the human in doing it, or is it going to be autonomous, maybe bring these fittings into it? What is the focus there?
We're trying to scope until when a robot could do what and what robot could be used there. But we're starting to approach this from the human-robot collaboration. So, for example, there is a lot of things that need to be held by 2 humans or more than 2 humans. They are very, very heavy. And robots could help in situations like this, or could substitute just by, them bringing things to the shipyard. So we're trying to assess, and this will take a lot into account the acceptance of robots in shipyards too, which is very unknown, basically. So we are conducting interviews with master shipyard people, so people that have a lot of expertise in doing this outfitting, and with novices, because robots can also be used to train the novices, which is a lot of time that they need to take to do that. So robots can also serve that bridge of education. So we literally just started like a month ago, so we're still trying to understand how to go about this, what's the big scope that we have here. And then we also know that outfitting is very different according to each ship, because it's not like there is a generalizable framework on how to do it. So what usually they do is they break down the tasks smaller and smaller, and then they assign people to each task in the outfitting, who puts the wires, the pipes, etc. And they go from there. But it could completely change with a new ship or with a new crew. And so we're also trying to find what is common here that the robot could do safely around humans.
Great. So more questions?
I can ask. Oh, sorry.
You can, okay, you first, and then.
Yeah, it's more a question because you talked about psychology and help for patients. Do your research also has help for patients with autism? Because I had read that it can help them get adapted to environments.
I have not conducted studies with autism, but there is an amazing researcher, Brian Scaselati, which I really recommend you to look into because he's the father of robotics and autism, basically. And I think autism is a very interesting domain, but also very complex because it's a spectrum, right? So they can be very heavily impacted by it, or they can be very functional. And so the results from it are hardly generalizable. But one thing we know from research around Brian Scaselati's work and other people working on autism and robotics is that autistic patients perform better socially, and they learn cues from the robots that they can generalize to human relationships. So one of those things is holding eye gaze when you talk to someone, right? Or doing less repetitive behaviors. They can be trained by a robot on these components, on these behavioral components, and we know that once they are trained in them, this new knowledge is transferable to how they interact with other people. Yes, thank you for the question. I think that's a very important line of research for sure.
Go ahead.
Yeah, so towards the very beginning of your talk, you showed this well-known examples of the circles chasing the triangles chasing the circle.
Yes, the classical psychology experiments.
Right. Do you know, is it known whether that's, so it's innate in us that we can recognize this as, say, bullying behavior or fear, or is this something that we learn?
So, this research in particular, I'm trying to find it again, was conducted with adults.
Right.
So I think to answer that question, we would have to do exactly the same with different levels of development, which I actually think no one did. And it would be very interesting to do. From children in different abstraction levels of their development, right? So concrete thinking, logical thinking, abstract, to teenagers, and even to older adults. How does our brain change? Maybe how does it change even if you enter certain stages of your life where you start to forget, so you have dementia, right? So could we start thinking about things differently?
The thing is that children, it is known that they very early start to understand intentions. Yes. Say a person going to a cupboard and they cannot open the cupboard, they understand, okay, they want in, and if they know how to open it, they help out. So there are studies like that. I'm not sure if there are children young enough with whom you can do this experiment and assume that they haven't had a chance to learn this yet.
Yes, we would need to raise them in isolation.
Right.
Which the medical board would accept. Yeah. But I think, my other question around testing this with children is, even if we can do what you're saying, right? Is their language matching what they're thinking? Can they really express everything?
Right. That's
so there's also that. So perhaps involving fMRIs and brain scans, because there are parts of our brain that light up when we are socially connected. And these are social brain connections, right? Could they light up for the same?
Well, okay, but I guess the data of which area corresponds to what is also from adults mostly. So who knows? Maybe
I don't know.
This is malleable and changes as we age.
Yeah, I think this is super interesting research. Actually, I invite you to read this paper. It's by Eider and Simmel from 1944, and it's very engaging to see, and it's still highly cited because of how generalizable this is among adults.
Thanks.
Yeah, thank you.
It makes us raise this question of why little babies after 2 months or so start randomly starting to smile.
Yes.
Right? Or certain things that just emerge. It's not mimicry necessarily, right? But I think but again, it's probably very hard to test the counter. You don't want to have a scenario where don't smile at them at all and then just have to, that will never be by any board approved, right? Or I think I've read, I'm not sure if that's true, if it's popular science, but I've read that there were these scenarios in Russia where they were keeping all the newborns in a separate space in a nursing home for.
Do you want these microphones?
It's all good. Oh, that's good. No worries. Works for now.
It's,
Yeah.
it's okay?
Yeah, it's okay.
You can do it also this one. Hold it. And now you can speak here.
Oh, okay, great.
Yeah.
So, you know, I read this, maybe you know it better, but I read that they were, for the first year of their lives, the child death was incredibly raised. Yeah, like something about this emotional connection. It reminded me when you were showing the survival, there were this slide, can you show it again? There was
Darwin?
yeah, so Darwin's adaptation was not at all, but it was also survival equals socialization. So I think there was a study I heard about where, in retrospective, because they were trying to figure out why were all these infants dying in communist Russia back in the days when all of the children were forced to go for the first year into these nurseries, and the mothers were forced to go back to work.
I don't know the details of this study, but I heard about it. I know another study that is related, which is around monkeys, because at the time they thought it would be okay to do this with monkeys. I don't think it's okay anymore. But they had these two monkey moms. So one was a fur monkey mom. Have you heard of this study? Some people. And the other was a wire frame monkey mom. So just wires that kind of would mimic a monkey. And the other one had fur. None of them was real, but the baby monkey was real. And so the one with the wires had nourishment, had food. The other one did not have anything. But they would keep always with the fur monkey mom, even though they could be starving, because of that sociability, the connection, the warmth, the potential of being hugged and protected. So I think there is a lot to say about socialization between human species, animal species, and I believe between our systems, our robotic systems, interactive systems, and our lives. And how they are built really impacts how we grow into, socialization and all of these aspects.
Cool. Okay, are there more questions? Otherwise, we would say we close it. Give a hand of applause to. Thanks.